This video is about antifragility, and in particular we're going to go over a couple of cases, specifically the scientific method and the process of evolution and why those are antifragile. But first, let's talk about a definition of antifragility. Antifragility is basically when something not only recovers from a negative shock, but gets stronger because of a negative shock. So it's really about a system's ability to adapt and to use the experience it has with negative shocks to develop resistance to future negative shocks. Now, antifragility is different from resilience. Resilience is about a system's ability to bounce back and recover from shocks, but resilience does not necessarily imply benefit from those negative shocks. So resilience is really more about repair and restore. For resilience, we might think of a car mechanic or a doctor. That really, it's about repairing damage and restoring to what it used to be. Now, on the other end of the spectrum from antifragility, we have fragility. And that's really where a system cannot encounter negative shocks, or it collapses under the weight of negative shocks. Now, we can think of body system examples. For example, a fragile body might be an older adult with brittle bones and whose body is kind of wasting away. That might be a fragile person, in which case that person is much more likely to die from the same colds and flus that children and younger adults might be able to handle with no problem. A body example of resilience might just be when we get a wound, that wound heals and goes back to the place just like it was before we got the wound. So that's resilience. It's not better, it's not worse, it's just fully healed. The body system example with antifragility is going to be weightlifting. So when we lift weights at the gym, the fibers in our muscles get damaged or sometimes even broken, but the real growth happens after we leave the gym when we're resting, when the muscle fibers sort of grow over the damaged parts or the broken parts to form new, stronger muscles. So in that case, encountering the negative shock of lifting the muscles and slightly damaging the muscles, that leads to stronger muscle growth in the long run. So that's an antifragile system in our body. Now, one interesting property of antifragile systems is that the more negative shocks they've encountered, the stronger they are, because they learn from each of these negative shocks. So you want systems that have been through the ringer. But when it comes to classifying systems as antifragile or fragile or resilient, it's not always super black and white. For example, it could be that a system looks fragile in the short run, but if you zoom back and look at a longer run, it's actually antifragile. And there could be some systems where it looks the reverse. So to look at this on a graph, it might look something like this. So the fragile system encounters a negative shock and is permanently weakened from encountering that shock. A resilient system might be temporarily weakened, but eventually it bounces back and returns to where it was before. An antifragile system might be temporarily weakened to a large degree or to a small degree, but then eventually it learns something from the negative shock and comes back more resistant to future such shocks. And then we have to think about the caveats here. So I gave this example of bodybuilding and how encountering these negative shocks makes our muscles stronger. But of course, if you lift too many weights at once, your body's going to be weaker afterwards. In fact, the whole bodybuilding process, even though it has some antifragile properties, it depends on encountering the right level of shock. So one caveat we need to be thinking about is the magnitude of the negative shock could make a huge difference in terms of whether the system ends up as a fragile system or an antifragile system. So that's one caveat. And really, we could think about it as it's possible to have a shock big enough that every antifragile system is going to end up collapsing under that shock. I mean, we might think of an asteroid like the one that killed the dinosaurs. We might think of these huge catastrophic events. Whatever antifragile systems we have in place are probably going to be destroyed by those shocks. So the magnitude of the shock is just one nuance to antifragility. And similarly, we could think about vaccines. Of course, with vaccines, you come out of the encounter with the vaccine stronger, and the vaccine, of course, is a weakened version of the illness that you're trying to avoid. and exposure to that weakened version makes you more resilient to future exposures to that particular illness, but that depends critically on having the right magnitude of the illness that you're exposed to. Vaccines need to be a very weak version of the illness, weak enough so that it's not going to make you sick, but strong enough so that your body actually builds up an immune system. And finding the right level of shock to create that antifragile response is actually one of the things that scientists have to think very careful about and test heavily for. So really, our first caveat is pretty important, that the magnitude of the shock matters a lot. And then our second caveat is that the time horizon matters. So maybe the system that appears fragile, we've just looked at a short enough time horizon, but if we watched it over time, maybe it's a person who's encountered a negative shock in their life, and they just need some time to grieve and to process and to learn from their experience of that negative shock, but eventually they will come back stronger than before. So maybe if we classify something as fragile, we do need to ask the question, are we giving this system enough time for the antifragile properties to kick in? And I love thinking of antifragility when it comes to people. When people encounter negative things in their life, illness, loss of a loved one, divorce, all that kind of stuff, they're going to go through a period where that weakens them for sure. But it can be really powerful when people come back stronger after the incident, after they've processed. But not everybody does. Some people stay in a fragile and weakened state forever, and in the long run they end up worse off because of the negative experience. It really depends on what happens down here in this negative, in this down cycle. What goes on in the system and in a person's sort of mind and heart down here is going to determine where they end up along these different possible pathways. So this is just a graphical depiction of antifragility with time on the x-axis and the strength of the system, which might be defined in many different ways. This could actually be a third caveat, is how do we define the strength of a system? Is it defined purely in its ability to handle future shocks? Or is there some other measure of strength that we might want to think about? So that's going to be our third caveat when we're thinking about antifragility. So our third caveat here is, how are we thinking about strength? What are the different measures we could use for strength? And would changing the measure of strength change whether something is classified as fragile or antifragile? So evolution is one of these antifragile systems, and one of the properties that we see in a number of different antifragile systems is this expand and contract pattern. So with evolution, of course, biological evolution, you've got your parents, they were successful, so they have a bunch of genes that were successful in the environment, but they generate a bunch of offspring that have a mixture of their genes with some random variations mixed in. Different mixtures between the father and mother, and of course, sometimes mutations of their own. So the expand generates a lot of children. We might think of a litter of kittens or a litter of mice. And that's the expansion phase, and the key characteristics here are they're kind of like their mother and father, but there's also some random variation. Those two key characteristics are going to show up in the expansion phase in a number of different systems. And then we have the contraction phase, where there's some sort of selection criteria that selects which of these is best suited for something. In this case, if we're talking about biological evolution, that's going to be fitness to the environment and sexual selection. So of these random variations generated by the parents of this litter of kittens, litter of mice, which of those works best with the environment that those mice are born into? And the contraction phase is going to select the best and only let the best survive to the next generation, so that the next generation has this as the starting point and will expand with the population that made it through the contraction stage. And this works well for antifragility because negative shocks can be part of the contraction phase. So if we think of a plague or an illness that hits a particular population, that's going to contract which organisms survived the plague. and the ones that survive are going to be more resilient to future plagues, in particular future plagues that have similar pathogens or similar characteristics of past plagues. And over time, the more plagues that population encounters, the more resistance that population is going to have to future plagues. So evolution is an antifragile system, and this expand and contract structure lends itself well to antifragility. Now let's see if this same structure can apply well when we're thinking about the scientific method. Well, it turns out the scientific method does have this expand and contract phase, except instead of generating organisms with random variations of the parent's genes, it's going to be hypotheses. So each of these might be a hypothesis that's generated from scientists' brains. So let me replace the father and mother with scientists who are deeply embedded in the current body of knowledge, and hypotheses they come up with that come out of thinking about that current body of knowledge. Alright, so we have scientists who understand the body of knowledge, generating slight variations on hypotheses that are slight variations away from the current body of knowledge. So it has these same properties where the new hypotheses are going to be kind of related to the existing body of knowledge, the successful body of knowledge that has survived this process of scientific testing over time, but we're going to get some random variation in that. And this is actually why it's important to have scientists from diverse backgrounds with diverse perspectives on the field, because a group of scientists who think differently with different personalities, different focuses, different understandings of the material are going to be able to generate a more creative set of hypotheses that build on the existing body of knowledge. So that's why diversity among scientists is going to be important, especially viewpoint diversity. And they generate hypotheses in an expansion phase. That's just coming up with a whole bunch of new ideas. And then we have the contraction phase, and this is the testing of the scientific hypotheses. We actually try to falsify any hypothesis. We scrutinize the data as we run it up against that hypothesis and think about that, and most hypotheses will probably not make it through the rigorous testing process, but those that do, those that were unable to falsify, become part of the existing body of knowledge that then a new generation of scientists learns the new scientific results, and they incorporate those into the way they think, and they use that as they generate more hypotheses. So the scientific method actually has a very similar expand and contract nature to it as does evolution. And this will also give it antifragile properties. For example, as we go through this expansion and contraction phase, we might encounter a negative shock, such as a piece of information that does not fit well or cannot be explained by the existing scientific knowledge, in which case that's a negative shock to our system of scientific understanding, and we're going to have to recover from that shock by putting new hypotheses through the system where there's an expansion phase and a contraction phase, generation of hypotheses, testing of hypotheses, teaching those hypotheses to the new generation of scientists who then generate more hypotheses. So that, of course, is going to have nice antifragile properties where the more anomalies that we encounter in the scientific world that we can't explain with the current body of knowledge, the bigger our body of knowledge will grow, the more resistant to future holes in the body of scientific knowledge. So the scientific method has a really nice antifragile property to it if it's done right. So just in summary, I hope you get from this video the fact that antifragility is more than resilience. It can be placed on a spectrum with resilience, where you've got fragility on one end, antifragility on the other end, and resilience in the middle. I hope you have some caveats in your head about why antifragility is more complex than it may seem at first. In particular, the magnitude of the shock might make a difference, and the time horizon over which you're evaluating a system might also make a difference in terms of whether you end up classifying it as fragile or antifragile. And then I hope the expand and contract phases in evolution and the scientific process have got you thinking about what properties make something antifragile.